So, hi everyone, my name is Andrei. I'm a PhD student at Institute of Science and Technology Austria, also called ISTA. Today, I'm going to present our latest work on large language model compression that was produced as a result of collaboration of our institute with Yandex Research, as well as the King Abdullah University of Science and Technology in Saudi Arabia. It's called Pushing the Limits of Large Language Model Quantization via the Linearity Theorem. And to start, let us first take a look at what the problem of LLM quantization is, how it arose, and what the state of LLM optimizations looks right now. So the idea behind quantization is that large language models have greatly increased in quality over the last few years, but a lot of the increase in quality came from the increase in the model size. And as a result, the cost of inferencing those models as well as training them has grown dramatically. And one of the results of it is that modern accelerators used to inference those models are always not able to run the latest models because they're limited either in their memory size or in the amount of compute they provide. More specifically, the memory is often the bottleneck in those systems, in a sense that modern large language models often have up to a few hundred billions of parameters, meaning that to run them in their native precision that they were trained in, you need a few hundred gigabytes of memory to store those models and inference them. And that's often not available to people trying to run them locally, or even to some GPU providers that end up having to run those models in a very parallelized settings where models are split between multiple accelerators in large data centers. So as a result, the field of model compression has emerged in the last few years, and it has more specifically has grown rapidly in the last few years. That aims to reduce specifically the model size, but sometimes also their cost of inference in terms of how much power, how much compute they require, and how fast you can infer them. But for this talk, focus mostly on model size, at least for now. So a few methods to reduce the model size, for example, include pruning, where model weights are selectively deleted from the model, resulting in smaller models that exhibit the same performance, or at least similar performance, but that require less memory to store, and sometimes even less compute to infer because of the representations that they use to store those sparse weights. But probably even more importantly and more widely used, quantization, which is a process of finding more efficient representations for models. And when I say more efficient, let us first look at what large language models are from a mathematical standpoint. So when we talk about a model, we usually mean that it's a function parameterized by some set of parameters. And those parameters are usually real numbers. And as I said, modern large language models usually have billions up to hundreds of billions of parameters, meaning that to store and run large language models, you need to store hundreds of billions of real numbers. And the way real numbers are usually stored on computers are floating point numbers. I will not go into details of what this representation is, but what you probably need to know is that for each floating point numbers on modern accelerators, you usually need 16 bits of information to represent one single real number. And this representation is good for many mathematical purposes because floating point numbers allow for a very wide range of numbers to be represented with good accuracy. But for purposes of machine learning, and more specifically large language models, this representation can always be redundant in a sense that it might have too much precision where we don't need it, and maybe there might exist more efficient representations on the number level that would allow us to achieve the same performance, but require much less memory to store. And the quantization is precisely about finding those representations that use less information to store every single real number, but retain the performance of the models. And when we talk about quantization, the simplest example we can think of is just representing numbers as integer numbers. And when I say integer numbers, let us think about a group of weights of real numbers that we want to represent in a quantized fashion with integer numbers. And we can take this group, we can scale and shift it operations that are negligible in terms of performance from the mathematical standpoint. We can make it such that all of those weights are within a certain range of numbers, for example, from 0 to 255. And if we then round the numbers, then all of the weights that we're representing would be integer numbers from 0 to 225, meaning that we can efficiently represent them and store them in memory as unsigned integers with 8 bits, meaning that we have just found a representation that with which we can represent all of our model's weights, but it used twice less memory than the original FP16 16-bit representation. And this was a very quick introduction into what quantization is, and to sum up, quantization is the process of finding more efficient from the memory standpoint and sometimes compute standpoint representations for our real numbers to allow us for the model to take less space in memory. And in fact, quantization is so popular that it has become de facto the standard way to run inference in large language models, because virtually all of the modern frameworks for LLM serve and support quantization in one way or another. For example, transformers and some of the adjacent libraries extensively support quantization in many different methods. VLLM, a very popular production deployment framework, supports it as well, many different quantization methods. Also, libraries like Olama and Llama CPP and XLama also all support quantization, sometimes different schemes, sometimes slightly different representations, but in its core, all of those libraries encourage the user to use some sort of quantization on top of the models to reduce their memory footprint and allow users to run those models on their device locally, which otherwise wouldn't be possible because of the memory limitations of users' devices. So when we were talking about representations, so if quantization is a more efficient representation for model weights, a question we could ask is, how do we find this representation? How do we obtain it? And in general, there are multiple answers to this question, because we can either obtain this representation as any other representation in machine learning and training the model from scratch in this representation, which would be called the quantization-aware training. And it's very compute intense. It's sometimes hard to make work from a mathematical standpoint, because algorithms training in weird representations often do not converge as nicely as trained to floating point numbers. So for the purpose of this talk, we'll leave out the quantization-aware training. And if we look at post-training quantization, which aims to find this representation given some model that has already been trained, and that is, let us assume, stored in floating point numbers, then we would have to find some sort of mapping from those floating point numbers to the representation that we want to use. And here we have to make an important distinction of whether we only have the model weights themselves to map into a quantized representation, or we have some additional information, either about the model architecture or about the inputs that are usually passed through this model. And for the purpose of this talk, at least for now, let us focus on the so-called zero-shot representation, where we only think of model parameters as real numbers in sort of vacuum, or at least in real numbers in some sort of groups of weights, but we know nothing else about the architecture of the model or what inputs are passed through it. And yes, one reason for why we might want to do that is because the more training we need to do on our quantized model, either training it from scratch or doing some sort of optimizations with respect to some sort of inputs to optimize our representation, the more compute we need for it, and the harder it is to generally obtain this representation. And on this scale, zero-shot quantization is the easiest from the point of point of view of how much compute it requires to obtain. And let us come back to model weights. So we now narrowed the scope of quantization to the fact that we only want to quantize weight themselves, and we do not really care about what role those weights play in the model, what inputs they're usually used with. But still, architecturally, models consist of different parameters, which can be either linear layers in large language models, embedding layers, or some additional normalizations and transformations on the model's internal representations. But if we take a look at the composition of normal large language models, for example, here we can see a plot for lemma 3.18 billion. We can see that still most of its parameters, so usually 80 to 95, maybe even 99% of model parameters, are usually simply linear layers. So what I'm trying to say here is that large language models are mostly consist of just linear layers. So when we're trying to design a new quantization method, often it is enough for us to only be able to quantize linear layers, because this is where the most profit from quantization, that is memory footprint reduction, comes from. And because simply all of the other parameters do not account for as much memory as linear layers themselves. So let us add a little more formality to this. So let us say that what we want to quantize is just some set of linear layers, that is some set of rectangular matrices that we want to quantize using just them and not any additional things like quantization over training or input over quantization. So now that we've narrowed the subject of what we're talking, so we're talking about zero-shot quantization of linear layers. Well, one natural question one might arrive to is that what effect exactly quantization has on model performance as a whole? And this is where the contributions of this work start to come out, because one of the first things we did in this paper is we studied the global effect of quantization, in the sense that we studied effect of quantization on different global metrics by which large language models are benchmarked. And those metrics can be very varied, because we can either look at some statistical language metrics such as perplexity, or we can look at more complicated metrics that involves reasoning or some sort of knowledge testing, so on top of large language models. Those metrics are often more representative. The more complicated metrics often better discern between good and bad models nowadays, because models are specifically trained for some sort of assistant roles to which reasoning and knowledge are core of how useful they are in practice. But for the purposes of this work, we mostly focused on perplexity and on statistical measures, because first of all, they're much cheaper to evaluate, because, for example, to evaluate perplexity with a model, you need to pass, for example, a few 100,000 or a few million tokens through it. But to evaluate some complicated reasoning benchmarks, the amount of tokens you need to pass through the model, and more importantly, generate one token at a time, it can be much larger. And in general, it can take up much more time. And the reason why we focused on perplexity is because perplexity is a smooth function of model weights in some sense, and it's less prone to noise. So small perturbations of model weights lead to predictably small perturbations of perplexity, which is not the case for reasoning metrics, which are usually some sort of true-false metric where small jumps are only possible by one answer, and in general, it's more prone to noise. So the first thing that we studied is to try and find the global effect of quantization. One thing one might do is quantize one layer at a time, to just try to understand how quantization of every single layer affects the global metric. So if we just leave the whole model as a whole, but take out one layer and start quantizing it, at what point does the model start degrading in performance? And in general, how can we describe how its performance as measured by global metric changes when we do quantization. And what we observed is that, as is the case with many physical systems in a sense, the performance at first changes linearly with quantization, which is kind of intuitive because this is what, for example, Taylor's expansion of our metric with respect to any abstract perturbation would say, that our performance changes linearly with how hard we quantize this layer. And moreover, we can see that this is the case with pretty much quantizing any layer one at a time. So what we observed is that for small quantizations, specifically, the performance changes predictably with how hard we quantize any layer in particular. And this can be described by sort of a linear model where we describe the metric increase for perplexity or metric drop for any other metrics where larger is better. It changes linearly with respect to how hard we quantize. On this slide, you can see how the perplexity metric changes with respect to quantizing three different layers. Each layer is quantized one at a time. For example, we can see that the down projection in the first transformer block is more sensitive. The model metric is more sensitive to quantizing this particular layer, and it's less sensitive to quantizing, for example, the gate projection of the 15th layer or the output projection of attention of the 30th layer. On the slide, we can also see that this linear model doesn't work for all the ranges of quantization, because we can see that for the harder quantization, it can explode after some point. For example, if we look at the topmost line around 1.5 bit per parameter, we can see that the quantization error starts to become larger than linear, which means that our effect is no longer linear and the errors start growing more rapidly with harder quantization, which is something you might expect for some layers, because degradations of some very important layers just would lead to metrics exploding and model outputs to just not be cohesive anymore. And for some layers, it's not the case, where the linear model is more robust and works for a wider range of bitwidths, basically. And so we observed what happens when we quantize one layer at a time. And another thing that we can think about is that what exactly is quantization, what kind of errors it introduces on this scale of one single layer. So if we take a look at a linear layer described by its way to WIK, then the operations that are used on it in practice is matrix multiplication with some input. And here we can see a single output channel described in this notation, where the output channel I is basically the input of the matrix multiplication between the weight and the input activations. And the quantization error for this particular layer, given that everything else in the model is frozen, can be described as the difference between those dot products of the quantized and the unquantized weights with the activations. And one can see that this sum is taking along all of basically the entire row of the weight metrics, which means that we sum up from hundreds to maybe thousands or 10,000 values in here that are also summed up with different size, because the quantization errors themselves can be either rounded up or down, and in general, those quantization errors can take a large range of values. But more importantly, they're still kind of the same scale, because if we take a look at a uniform grid, then all of the errors that we talked about are still on the scale of between two values in this grid. So we're summing up, what I'm trying to say here is that we're summing up a large amount of values that are of similar scale, but also somewhat uncorrelated because the quantization error for adjacent weights can be more or less arbitrary. So some weights get rounded up, some weights get rounded down, and there isn't a strong correlation between those weights. So one thing one could expect is that the errors within one matrix multiplication gets added almost in a random fashion, and that the total error could probably be described by something similar to a central limit theorem, where the quantity that really matters to the scale of the final error is the mean square error of the quantization of each value in particular. Because when you add a lot of similar but independent random variables, the resulting distribution of the sum would be close to a normal distribution that is characterized by the variance of the distribution of its elements, where here each element would be a quantization error of each particular value, which means that what's really important is the mean square error of quantization of each particular value in this matrix. So this was the first insight that we had with respect when trying to describe what effect quantization has. And the second effect is that we can once again look at this plot where we can see that with respect to every single layer in isolation, the quantization error is the quantization error's effect on the resultant metric is pretty much linear within some range of parameters, within some range of how hard we do quantization. And what we could try and theorize is that those effects add together also linearly, and this linear model can be applied not to one layer at a time, but to the whole model as a whole. And what I mean by that is that perplexity, for example, here, where the main metric that we focused on is perplexity, can be described as the perplexity of an unquantized model plus sum over all of the linear layers in the model with some coefficients, how much they're quantized. Here, again, as I said, since mean square error of quantization is theorized to be a very important property, we use this mean square error as the basically the describing property of this linear model. So the linear model that we built explains a linear dependence of the resulting metric that we focus on the basically mean square error of quantization of every single layer separately. And we built this linear model, and we tested whether the predictions of this linear model check out with what perplexity values we get in practice. And what we saw is that there is a limit to this linear model in a sense that it accurately predicts the perplexity up from 3 bits per weight. But as we saw with one of those plots and with the whole model in particular, and the whole model as a result, the perplexity explodes below some threshold because the linear model is just not applicable in the regions with quantization that is of that introduces errors of certain scale. So what I'm trying to say here is that we verified our linear model when we first sort of fitted the coefficients alpha by quantizing one layer at a time, and then used this linear model with the now known coefficients alpha to quantize the whole model and look at what perplexity will have in practice and what we'll have as a prediction of this linear model. And we observed that the prediction matched the actual perplexity up from 3 bits per parameter, but the perplexity in practice was higher for harder quantization below 3 bits per parameter. So what we did then is that with those insights and this practical verification of the model that we built, we formalized a theorem that would support this claim that mean square error is really what we should be focusing on when doing quantization, and that the quantization errors add up linearly between the layers. And with a number of assumptions, we mathematically proved that this is indeed the case for large language models. We had to make some strong assumptions. For example, assumption 3 here says that the hashing of our model with respect to a metric that we're trying to describe has to be close to block diagonal, but we ran some additional experiments trying to estimate this hashing and show that in practice it is indeed usually pretty close to diagonal metrics. But the point of this slide is that we not only verified our linear model experimentally, but also provided some mathematical justification for why it's true. And those quantities specifically, the MSE error of quantization specifically, is the quantity that affects per metric drops as a whole when doing quantization. So to recap this part, quantizing each layer at a time independently, we can see the linear relation, and we can theorize that the linear relation between the metric change and how hard we quantize. And we can theorize that this linear relation extrapolates beyond quantizing one layer at a time, but quantizing the whole model together. And we verified this conjecture both in practice and with the theorems that we formulated and proved. So with those findings, we can proceed to actually exploit them to construct better quantization methods. And the first consequence of that finding is that we propose a new quantization method dubbed HIGGS. So let us reiterate what we found in the previous section. We found that the global metric changes can be described as a linear model with respect to mean square error of quantizations of linear model weights separately. And what that means is that this quantity, this quadratic error of quantization, is the quantity that we want to optimize when doing quantization, because it will lead to improvement of the metric on the whole model as a whole. And let us come back to the essence of quantization once again. So quantization is finding a more efficient representations for our floating point weights. And how it's usually done is that weights are rounded off to some sort of grid in the space of natural numbers. That is, instead of using floating point numbers to represent weights, we now used some sort of fixed set on the fixed subset of real numbers, a finite fixed subset that we round our values to have a representation that uses less information than floating point numbers themselves. And we already looked at uniform grids and how they can be obtained, but it's not clear why uniform grid should be the best we can do in terms of minimizing this quadratic error. So now we have a very definitive goal that we want to minimize the quadratic error, and maybe some sort of slightly different grid that better fits the distribution of our values would lead to smaller quantization error in general. And a few ideas have been proposed of using a more complex grid, a grid better optimized for weight distribution. For example, normal float was proposed by Tim Detmers and co-authors to better map the weight distribution onto the grid that you're trying to round to, but they didn't try to optimize the MSE, the L2 error. Instead, they optimized the entropy of the result in quantization, meaning that they make it such all of the quantization grid points are used more or less evenly with respect to how many values are quantized to them. In contrast, abnormal float was proposed by Yoshida that optimized the grid such that it minimizes the L1, the absolute reconstruction error, the absolute quantization error, to better, again, to fit to the weight distribution. And to minimize, to optimize the grid with respect to some metric, we need to first assume some sort of weight distribution. So we, a priori, we don't know how our weights are distributed, but if we look at them in practice, we'll notice that they're kind of similar to Gaussian distribution. And what Tim and Yoshida did, as mentioned on the previous slide, they actually assumed that the weights are Gaussian distributed and optimized the quantization grid such that it optimized either the entropy of rounding this distribution to this grid or the L1 error of rounding this Gaussian distribution to the grid. But there have been, but as we can see in this slide, this distribution is not perfectly Gaussian because first of all, it got slightly heavier tails, and second of all, it has some sort of outliers in the center. So it's some sort of peak that is not usual for the Gaussian distribution. And during the past few years, a few methods have emerged to actually stabilize the weight distribution and get rid of both the heavy tails and the abnormalities in the center of the distribution. And one of those methods is the Hadamard transform. Hadamard transform, what it is basically some sort of random rotation that you perform on the weights to make the distribution of the resulting metrics Gaussian. So it basically guarantees that after you apply this sort of transform to your model weights, the resulting distribution of your weights would be Gaussian. Although as it is some sort of rotation, it slightly complicates how you would actually run inference on this model because it incurs some minor runtime costs on actually using this changed representation in practice, but those runtime costs are usually negligible. For now, let's just focus on the fact that there exists a way to guarantee that the distribution of the weights of the model that you're trying to quantize would be Gaussian. And to reiterate what we have, we know a quantity that we want to optimize. We want to optimize the quadratic error of rounding your weights to a certain grid. Moreover, you can guarantee that your weights would be Gaussian distributed. So what we propose is that, first of all, we apply this Hadamard transform, this preprocessing on our weights to guarantee that it be Gaussian distributed, and we design a grid such that it minimizes the quadratic quantization error when quantizing a Gaussian distribution to this grid. And there have been a number of papers that use some of the ideas that I've mentioned. For example, if we specifically look at the second point on this slide, the Hadamard weight preprocessing, it has already been used by a number of papers for LLM compression. For example, Quip Sharp and Carrot both use the Hadamard preprocessing on the weights to make them Gaussian distributed and make them more easily quantizable. Moreover, the idea of MSE optimal grids over the Gaussian distribution isn't new either, because, for example, it was proposed as a method for distributed mean estimation by Wargowski and co-authors, and even for solving partial differential equations by Pages and co-authors. And so to reiterate what our method comprises is that it uses Hadamard and coherence to guarantee that the weights that we're trying to quantize are Gaussian distributed, and then it uses MSE optimal grids to quantize those weights. In total, results in very low MSE quantization error that we want to minimize because our theorem states that this is the property you want to minimize for every single layer in order to obtain the lowest global error possible. Also, our method incorporates one other idea that has been present in the field of LLM quantization for some time, that is vector quantization. So previously, when we talked about quantization, we talked about grids as some sort of one-dimensional set, where grid is basically a set of points, and when you quantize a real number to a grid, you take one number and you select the point from this one-dimensional grid to represent it. But in practice, what you can do is you can construct multi-dimensional grids where you would, for example, round every two numbers to some sort of grid point in a two-dimensional space. And our method can be extended to allowing for vector quantization. That is, that our grids would not just be optimal for a single dimensional Gaussian distribution, but rather for a multivariate Gaussian distribution, for example, two-dimensional, three-dimensional, or four-dimensional, and will be quantizing weights in groups of 1, 2, or 3 weights by projecting them into this grid. And as we can see on this slide, the performance of our method improves as we increase the dimension of our quantization. As we can also see on the left-hand side of this slide, is that when we increase the dimensionality, so the leftmost picture here depicts the basically one-dimensional grid, or rather the product between two of those grids to represent values. And we can see that when we actually produce a two-dimensional grids, that is not just a product of lower dimensional grids, it can be better fitted to a Gaussian distribution, leading to a smaller quantization error in general. And yes, the right-hand side of this slide illustrates how increasing the dimension improves the overall performance of the model, as demonstrated again by Victex perplexity. And we can also see that our method, HIGGS, overperforms the previously existing methods such as normal float and abnormal float that we mentioned earlier, that minimize the L1 reconstruction error or and maximize the entropy, as mentioned before. So we discussed what our proposed method is, and now we shall discuss how to actually use it in practice. So the representation that we obtain is basically we have some sort of complicated grid that is not anymore just a uniform grid or natural numbers, but rather just some abstract grid in one-dimensional, two-dimensional, three-dimensional space, as well as selection from this grid that encode which grid point were some groups of values rounded to. And to actually run any sort of inference on top of this representation, we have to restore it into floating point numbers, because modern hardware can only perform matrix multiplications and other arithmetic operations with floating point numbers. At least let us say that for the purposes of this talk. So we'll have to somehow restore, obtain the original floating point representation from our complicated representation in order to do matrix multiplication. And for that, we can write optimized kernels that would basically overlap this dequantization procedure with the matrix multiplication procedure for it to be more efficient. So what I mean more specifically by it is that matrix multiplication is usually done in blocks on modern GPUs and some other accelerators, where for every block of the matrix that you're multiplying with, you iterate over blocks of the other matrix and write the output. And what you can essentially do is not dequantize your whole matrix and then the multiplication, but insert the dequantization procedure inside those blockwise multiplication operations for it to be more efficient in practice and better utilize both your computation kernels and your memory bandwidth. And this was done by Guo and co-authors in their paper, where they introduced the flute kernel that effectively overlaps this dequantization procedure, specifically the lookup procedure, where for each point in the grid, and in encoded selection, you restore the original weights by doing a lookup into this grid. And they merge this operation with matrix multiplication to achieve great speedups over the original floating point multiplication, mostly because the lower bit width of the representations allowed them to more efficiently utilize the memory throughput, achieving greater end-to-end speed for large language models. What we did in our paper is we adapted the fluid kernels to allow us to use vector quantization. Those kernels were initially developed to only allow for scalar quantization, meaning one-dimensional, only for one-dimensional grids. But with some modifications, we were able to modify it to use two-dimensional grids because, as I described earlier, using more dimensions allow us to achieve lower quantization error and better performance in general. And what we showed is that those kernels still retained practically all of their speedup, achieving speedups over FP16 in a large range of bit width and a large range of batch sizes, which is not the case for some other kernels, for some other quantization methods that usually only focus on batch size equals 1, which is arguably more important for decoding, but still is a limitation for more parallelized workloads or things like speculative decoding. So what I'm trying to say here is that the fluid kernels are very efficient across large range of bit widths, allowing us to quantize to either 2, 3, or 4 bits. They are efficient across a large range of batch sizes, allowing to run efficient parallelized inference or speculative decoding. And they also allow for vector quantization, which means that they can achieve better performance in terms of quantization error than many other kernels. So to recap this section, what we did is that we proposed a new quantization method dubbed HIGGS that incorporated vector quantization, Hadamard weight preprocessing, and MSE optimal grids into it to allow for smaller quantization errors than previously existing methods such as normal float and abnormal float. And also we have extensive kernel support for this method that allows us to run it efficiently across a range of bit widths and batch sizes. So, as I said, this is not the only application of the linearity theorem that we found, because we can also solve the dynamic bit width quantization problem with it. And when I say dynamic bit width quantization, what I mean is that for every layer in the model, we usually have a number of options how we can quantize it. Let us think of those options like a set of quantizers that we use. For example, we have a quantizer for 2-bit quantization, 3-bit quantization, and 4-bit quantization. And for every layer, we want to select one of those quantizers to quantize with. And the target that we want to minimize is that we want to achieve the best performance that we can. But one natural thing would be that you can always use basically the best quantizer for every layer. So we can, but there is a trade-off in the sense that better quantizers usually use larger amount of bits to encode values. So a natural constraint on this problem would be to put a constraint on the total average number of bits that we want from our quantization. For example, if we quantize half of the layers to 2 bits and half of the layers to 4 bits, we would achieve 3 bits on average, which means that we would, yes, we would achieve 3 bits on average. But what I'm trying to say here is that some layers have, as we have seen with the linear plots of the dependence of metrics with respect to how hard we quantize, are more sensitive to quantization to others. So it makes sense to quantize some layers harder and quantize some layers less. So by allocating those bit widths differently between different layers, we can actually achieve lower global error if we quantized all of the model to 3 bits, for example. So let us think about this idea once again. So different layers have different sensitivity to quantization, as we can see on this plot. So some layers generally exhibit more metric drop than others at the similar quantization level. And we described this effect with the linearity theorem that said that the global metric change can be described as a linear sum of quantization errors of different layers. And we can estimate the alpha coefficients in this linear model by just quantizing one layer at a time and estimating the linear coefficient in the dependence of the metric with respect to how hard we quantize in terms of quadratic error. Yes, as I said, we can basically fit those linear dependencies to obtain the alpha coefficients. And let us take a look at this problem again. So we have a constraint on the total bit width, the average bit width that we can use. So we have some sort of budget that we can operate within, and we want to minimize the perplexity or global metric. And using the linearity theorem, we can actually rewrite this optimization problem as just minimizing this quantity, which is basically the linear part of our linearity theorem. And if we take a look at this problem, we can see that this is not a complicated problem from a mathematical standpoint, in the sense that this is some variation of a knapsack problem where we have a constraint on the total budget that we could use, and also some linear coefficients with respect to how much each layer contributes to the total quantity that we want to minimize. And actually, this can be reformulated as either a linear programming problem or some other standard types of mathematical problems. And if we reformulate this problem as a linear programming problem, we can use existing solvers like SAT to solve it within literal seconds, which means that we can find an guaranteed optimal solution to this problem within seconds. And if we look at what this solution would look like with respect to our budget of quantization, we can see that the higher our budget is, for example, if we use the higher our budget is, the lower perplexity increase we can achieve. For example, at 6-bit, we get about 0.01 perplexity increase. With 4-bit, it's about 0.2. And below 3 bits, it starts to explode and lead to huge perplexities. By the way, on this plot, we can see the points are the actual perplexity measurements for the solutions of this problem, and the dotted line is the linear model prediction. And we can see that down to around 3 bits per parameter on average budget, the predictions of the linear model agree pretty well with what we get when quantizing to those complicated dynamic bit widths in practice. So maybe to summarize what we did here is that we took a standard problem of dynamic bit width quantization where we want to minimize the total perplexity increase given some sort of average bit width budget that we can use. And we basically boiled it down to a linear programming problem that we can solve very easily. And we did it by applying our linearity theorem to the problem of dynamic bit width quantization. So one thing about this is that is our method data free still, because as I said, we are using zero-shot quantization on the weights, so we're not aware of any inputs to the model when we actually do the quantization, but actually implicitly we still use the data in a form of metric that we're fitting the coefficients alpha with, because to obtain the coefficients alpha, you need to measure to quantize layers one at a time and measure the metric, and the metric itself carries some sort of data. So this method is not data free anymore because it uses, for example, Wikitext perplexity to obtain those coefficients and then optimize using those coefficients. But as such, for example, if we fit coefficients alpha on Vickitex perplexity, then Vickitex perplexity would not be a fair metric to compare on later on, because we sort of tune onto this metric when we do the quantization itself. One thing we could do is just replace Vickitex perplexity with some data-free metric like KL divergence between the original model's outputs and the quantized model outputs with respect to some randomly sampled tokens, which would make this method, first of all, data-free, and second of all, would make it such Vickitex perplexity would still be a metric that we could do a fair comparison with other methods on, because we do not use it, the Vickitex data at any point during quantizations anymore. And so let us take a look at the results that we got with respect to both the Higgs quantization method itself and the dynamic bitwidth quantization method that we propose. And first of all, one thing we can see is that Higgs basically outperforms all previously existing zero-shot quantization methods, including normal float, abnormal float, and also the HQQ method that came out last year. And it outperforms them across a large range of bitwidth. So both at 3, basically from 3 and up to 4 something bit with quantization. But one more interesting thing we can notice is that the dynamic data-free method that we proposed for dynamic bitwidth quantization gives us a consistent improvement over Higgs itself, adding 1 or 2 points of, for example, memory perplexity consistently as well. Also, an interesting part of this results table is that if we compare our data-free method or even just a zero-shot non-dynamic method with the GPTQ, a very popular one-shot quantization methods that uses more compute and is more computationally complicated because it uses some information about model inputs to do the quantization, we would see that Higgs still outperforms GPTQ by a large margin across those bitwidth. But one thing one could ask is that GPTQ is a method that basically uses some input information to linear layers in forms of the hashing of some quadratic problem to minimize the quantization error in a more complicated manner. And what it practically does is that it does round to nearest quantization on every column of model weights, and then does some smart optimizations on the remaining unquantized weights that, yes, have not been quantized yet. And in general, we could do this projection step. When GPTQ was designed, it used the projection onto a uniform grid, a one-dimensional uniform grid. But what we could do is that we could replace this projection with the projection onto a Higgs grid to allow it to do a vector quantization with Higgs grid. And what we would see is that it would be pretty easy to implement because we would also have to modify the projection step itself, but it would allow us to achieve consistent improvements over both GPTQ and Higgs themselves, almost reaching the performance of some state-of-the-art one-shot quantization methods that has come out since GPTQ. For example, QuipSharp is a method that came out a year ago, and it also uses Hadamard preprocessing as well as some very complicated symmetrical grids to achieve low quantization error. And we can see that GPTQ plus Higgs, which is a straightforward combination of GPTQ and Higgs, outperforms QuipSharp at 3 and 4 bits, but still loses at 2 bits. And QTIP is an even more complicated method that uses trellises quantization and is in general much more computationally demanding than all of those methods. It's still much better than GPTQ plus Higgs at the low bitwidth quantization, but is pretty similar at 4 bits and above. So with that, I'm done describing the new methods and ideas we proposed in this paper. And the last thing that I want to mention is that our method is already integrated into Hugging Face transformers. Right now, it's in some sort of testing phase where we only support a small number of architectures. We support Llama 3, including 3.1 and 3.3 models. and the gamma models, and also all of their fine tunes. And when I say we support it, I'm saying that you can do zero-shot quantization out of the box, just as bits and bytes integer rate or NF4, where you just give us the checkpoint of an unquantized model and a quantization config, specifically a Higgs quantization config, and the model would be quantized on the fly within literal seconds or maybe minutes for larger models, and you would have a fully quantized model running locally on your machine, utilizing those efficient fluid kernels I talked about that are efficient and actually faster than bits and bytes and the GPTQ at low as well as at batch sizes equal to 1 for generation, or it's even batch sizes larger than 1 for speculative decoding and parallelized use cases. So with that, I'd like to conclude my talk and thank everyone for inviting me here to share my research with you. It's been a pleasure. And